Welcome back, guys. Just want to say congratulations. You've made it through college algebra. We're about to start our last lesson of the semester. We have a very special guest who decided to drop in to come hang out. Little Snoop Dogg over here, my man. He's pretty excited about our last lesson, and he's been pretty excited throughout the entire semester, learning all this really good stuff about algebra. I hope you guys have too, and make sure that you guys come back and look at these videos while you're preparing for the final exam, and when you go on to take pre-calc and trig and calculus and all those other really great classes, hopefully you'll take some of the stuff and you'll remember it. If you ever need a refresher, email me. I can send you a link to the video if you want to rewatch them down the road. So let's get into it. We're going to be looking at applications of exponential and logarithmic functions. In our previous lesson, we were solving exponential and log equations. So we're going to be using those same ideas here. But when we're dealing with applications, obviously, there's typically a word problem involved. The first application we're going to look at is a financial application. So we've got two formulas, compound interest and continuous compound interest. And just to give you some information about that, so you have an idea of what we're talking about. Most of us have actually had some type of an account that accrues interest in a compounding fashion. If any of you have ever had a credit card, when you purchase something on a credit card, at the end of the month, whatever you haven't paid back, you pay interest on it. Well, at the beginning of the next month, if you still don't make any payments on it, at the end of that second month, they're going to charge interest again, but it's not just on the initial amount borrowed, it's on the initial amount borrowed plus the interest at the end of the first month. So that's how we start seeing this huge increase in our credit card bill when we don't make any payments on it. So that's our compound interest, and continuous compound is the same type of problem. It's just instead of being compounded a fixed number of times per year, it's always compounding. So you have these formulas. Hopefully you're familiar with them. Let's review just the variables here. A is going to be our future amount. P is our principal or the initial amount. R is our interest rate, our annual interest rate. Anytime we are using a rate in a formula, we need to make sure that we convert it to its decimal form. N, in just our compound interest formula, relates to the number of times that account's going to be compounded per year. And T is our time. When we're dealing with a financial application of exponential functions, time is always going to be measured in years. Now, this is important because if a problem says find the amount after 6 months, we need to convert that time in months to years. So we would plug in T equals 1/2. Find the future amount if $1,200 is invested in an account earning 6% annual interest after 2 years that is compounded monthly. If my account is compounded monthly, what is the value of N, where N represents the number of times it's going to be compounded per year? Well, there are 12 months in a year, so N is going to equal 12. So we plug our values into our formula. A is what we're trying to find. That's our future amount. Our principal was $1,200 times 1 plus our interest rate was 6%. So its decimal form is 0.06 over n, which is 12, raised to a power of 12 times t, or 12 times 2. Now, before you type this in your calculator, I would encourage you to do some mental math on your own. Specifically, 12 times 2 is 24. And when you're typing this in, you might be able to type the entire thing in all at once. Otherwise, simplify inside the parentheses first, then apply your exponent, and then multiply by your coefficient of 1200. When you do this, you should get an amount of $1,352.59. Now in the next example, we're going to use the same values, but we want to investigate the amount if the account is only compounded quarterly. Now, what do you think is going to happen with our future amount? Do you think it's going to be more or less than when we compounded monthly? Since we're compounding fewer times in a year, quarterly is n equals 4. You're not going to have as much time to earn interest on previous interest, so we should have an amount that is less than what we had in our first example. Plugging our values into our formula, A is equal to 1200 times 1 plus, our interest rate remains the same, so 0.06, but now we're dividing that by 4, raised to a power of 4 times 2. Again, the time is remaining constant. Simplifying that exponent, 4 times 2 is 8. Now we can plug this into our calculator. When you do that, we should get $1,351.79. So as we predicted, our future amount did decrease when we had fewer number of times compounded per year. Find the future amount if the account is compounded annually. If it's compounded annually, the number of times it's compounded is once. If it had said semi-annually, that would have been twice. Daily, 365 days. There's an interesting fact. If an account is compounded daily, there's something called the banker's rule where they actually only compound it 360 times per year. So, interesting little bit of trivia for you. Back to our problem, substituting our values, 1200 times 1 plus 0.06 divided by 1, raised to a power of n times t, or 1 times 2. And a lot of this we can simplify. This is going to be 1.06 squared. And when we plug this in, we should also see another decrease because we're compounding even fewer times in this example. Our future amount is $1,348.32. So although it's not a drastic decrease in our future amount, we are still seeing that future amount gets smaller as we decrease the number of times we compound per year. If our account is compounded continuously, now we're shifting gears. We're actually going to use that other formula. A lot of times we just call it APERT. Our principal is 1200. E raised to a power of 0.06 times 2. Again, try to simplify what you can. This is 1200 times e to the 0.12. And then, again, use your exponent or evaluate exponents first and then multiply. We should get an amount that's even higher than our first initial amount when we compounded monthly. Compounding continuously is always compounding, so way more than 12 times per year. We get $1,353, and it rounds out to an even $1,353. Next, we'll look at exponential growth and decay. With exponential growth and decay, we're talking about all sorts of things, populations, the growth of bacteria, things like that. And we'll see lots of really cool examples of this. There's an entire little group of mathematics or sector of mathematics that just deals with this type of modeling. It's really important in terms of data collection. We look at it in all sorts of examples. So, for example, if I'm thinking about or I'm planning a school, I'm going to watch the growth of the students so that I can eventually make predictions on how many students are going to be around or enrolling in 10 years. If the enrollment increases so much that I need more facilities, then I want to know that 10 years out so I've got time to raise money. So this modeling is very, very crucial in all sorts of aspects of our world. With our formula, if you look at this is our exponential growth and decay formula. We'll talk about how we differentiate between growth or decay in a second. But what does this formula look a lot like? Look at your previous slide. This looks a lot like your APERT formula. And they're exactly the same formula. Absolutely the same. Our A is the future amount or future population, whatever it is. This A with the little subscript of O, that's read A naught. That's your initial population or your initial amount. T is our time. When we're not dealing strictly with a financial application, time can be measured using any units. So days, weeks, hours, minutes, it doesn't matter. Only when we're talking about a financial application are we always going to measure time in years. And then K. K is really special. K has to do with our growth or decay parameter. Notice I'm not using the word rate because it's not a rate. It's related to how the values are changing, how that population is growing, but it's a little bit different. So we want to make sure we're very, very careful with how we label this. So we can call it the growth or decay parameter, or we could call it the growth or decay factor. It's a constant that, again, is related to how your population is growing or decaying. If K is positive, then we're going to have growth. If K is negative, then we'll have decay. The number of shares of a certain Facebook post doubles every 5 minutes. If 15 people have shared the post at 9 a.m., how many people have shared the post at 10 a.m.? Now, let's look at this. They're talking about this post, and every 5 minutes that's going to double. So that has to do with the rate at which this is increasing. Yes, but this is not what our growth parameter factor is. The first thing we're going to have to do is actually solve for K. We're using that exponential model, A equals A naught e to the kt, but we don't have our growth parameter. We're going to have to solve for that, and that's how most of these problems start. You're going to end up solving for K first and then solving whatever question it is that they're asking you to solve. Only if it says very specifically the growth parameter or the growth factor is equal to whatever the value is, can you assume the value of K. You'll see it a couple times in your homework, but you'll know the difference. They're going to be very specific when identifying the value of K versus just talking about how the population is changing. So the first thing we want to do is find K. We're going to need some points in order to find that. And when I mean points, the values that are represented by the relationship. So at time 0 or 9 a.m., how many shares had there been? There had been 15 shares of that post. Now, if it doubles every 5 minutes, after 5 minutes, how many shares are there going to be? There's going to be double the initial amount, or 30. This is our time. This is our amount. When time is 0, that gives us our initial amount. Since we're no longer dealing with a time of 0 here, they're saying that when the time was 5, there were 30 shares. So we can plug all this in. 30 is equal to 15 times e to the k times 5. Because after 5 minutes, there were 30 shares of that post based on the fact that it doubles every 5 minutes. So here we have an exponential equation, just like we saw in our previous video, that we can solve for k. We're first isolating our exponential term by dividing both sides by 15. 30 divided by 15 is 2, equals e to the 5k. And now, since our base is e, we're going to use the natural log. Natural log of 2 equals the natural log of e to the 5k. And again, recognizing our inverse property of logarithms, the natural log of e to the 5k is simply 5k. Divide both sides by 5. We get our value of k. Let me see if you can still see this. There we go. The natural log of 2 over 5. And we're going to leave this as an exact value like we have here. So now we can take this and plug it into our model. The future amount of shares is equal to our initial amount, which was 15, e to the natural log of 2 over 5 times however much time. Now we want to find how many shares were there at 10 a.m. Well, if it's 10 a.m., how much time has passed? You got to be really careful. We have to be consistent with how we're measuring time. We don't have to do it in years, which is obviously not going to be relevant here, but you have to be consistent. In our previous step, how did we measure time? We went from 0 to 5. 5 what? 5 minutes. So if I started at 9 a.m. and now it's 10 a.m., how many minutes have passed? 60. So we're going to use t equals 60 to solve for a. Now you've got to be very careful when you're evaluating this. I would suggest plugging this into your calculator, multiply natural log of 2 over 5 times 60 first, and then raise e to that answer. Take that answer, multiply it by 15. When you do that, you'll get a nice pretty number of 61,440 shares, which is pretty remarkable. I'm sure you guys have seen those posts on Facebook. I'm trying to teach my students about how quickly things spread on Facebook. This is evidence. In 1 hour, we went from 15 shares to over 60,000 shares. Imagine what would happen in an entire day. So you guys could figure that out using this model here. Again, if you're having issues with typing these expressions into your calculator, bring them to my office, bring them to class, and we can look at it together. Morphine is a common drug used to relieve pain. The half-life of morphine is 2.5 hours approximately. If an individual is given 15 milligrams at noon, how much will be in their system at 4 p.m.? So again, we're being told something about how the amount of morphine in a system is decreasing. When it says half-life of morphine is 2.5 hours, that means every 2.5 hours, there's only half of what was originally there. So we're given something about how it's decreasing, but we're not given the value of k. That's where we start. We first find k. So we're going to use 2 ordered pairs to determine that. Again, we're separating our points, time and amount, time and amount. Well, we know initially the person had received 15 milligrams of morphine. And we know that after 2.5 hours, there's going to be half of that. So if there's half of 15, we have 7.5 milligrams of morphine. We can plug that into our model. A equals A naught e to the kt. Our future amount's going to be 7.5. We started with 15, and that 7.5 occurred after 2.5 hours. Solving for k, just like we did in that, previous example, start by isolating your exponential expression. Divide both sides by 15. 7.5 over 15 is 1/2. And now we're going to take the natural log of both sides. The natural log of e to the 2.5k simplifies to 2.5k because of our inverse properties. Equals the natural log of 1/2. Divide both sides by 2.5. And we have our value of k. If we plug that back into our model, A is equal to, our initial amount was 15, e to the natural log of 1/2 over 2.5 times t. They want to know how much morphine will still be in that individual system at 4 p.m. Take a look at how you measured time initially. We measured time in hours, so we'll continue to use hours when we're solving here. At 4 p.m., if we started at noon, 4 p.m. is 4 hours. So plugging in, we have 15 e to this value of k. Make sure that you're using an exact value of k. Just the slightest change in that value, if you round it in the middle, can make a pretty significant difference at the end of the problem. So be very careful, use that exact value. Don't use a rounded decimal. Again, I suggest find what this number is, the natural log of 1/2 over 2.5, multiply that by 4, raise e to whatever that value is, and then take that answer and multiply it by 15. Rather than trying to type all of that in your calculator at once, it's going to be really hard to see all of that, so you're not going to be sure if you have parentheses where you need them or not. When we solve this, we should get 4.948 milligrams. Now you can check your answer pretty easily in terms of whether or not it's reasonable. If we had gotten a value greater than 7.5, we know that that's not reasonable because more than 2.5 hours had passed. So we should have less than half of what we originally had. If we'd gotten a negative number, also not reasonable. We can't have negative number of milligrams of morphine. So make sure that you think about your answer and check to make sure whether or not they make sense based on the context of the problem. Our third application is Newton's law of cooling. We all experience this. We take something out of the oven, we set it on top of the stove, and eventually it will start to cool off. Well, that cooling occurs following this model. Going over our variables, U is equal to the temperature of the object after a certain amount of time, or the future temperature. The capital T is the temperature of the environment. I'm sure that we would agree if you take your casserole or cake or cookies or whatever they are out of the oven and you just stick them on top of the counter, they're going to cool a lot slower than if you were to take them out of the oven and put them in the freezer. That has to do with the temperature of the environment. U naught is the temperature that your object was heated to. Lowercase t is time. And K is our rate of cooling. Again, just like with our previous problems, typically they're not going to give you the value of K explicitly. You're going to have to solve it using some data that they had already given you. An object is heated to 110 degrees and then is allowed to cool in a room whose air temperature is 22 degrees. These are in Celsius. If the temperature of the object is 85 degrees after 6 minutes, when will the temperature be 50 degrees Celsius? Let's go ahead and rewrite our model. It's capital U equals capital T plus U naught minus capital T multiplied by e to the kt. What values are we given in the problem? The object is heated to 110 degrees. That's our U naught. Is allowed to cool in a room whose air temperature is 22 degrees. That's our capital T. The temperature of the object is 85 degrees after 6 minutes. So here we've got our time and our future amount. So now we have an equation with just one variable K. We can solve this to find K and then use that to find when the temperature will finally reach 50 degrees Celsius. So solving this, we want to isolate our exponential term first. So we're going to have to subtract 22 first. (110 minus 22 is 88. E to the 6K. Divide both sides by 88. We have 63 over 88 equals e to the 6k. Again, we want to make sure that we're not rounding any of these values, so just leave them how they are. We'll take the natural log of both sides. The natural log of e to the 6k is 6k. That equals the natural log of 63 over 88. And we'll divide both sides by 6 to get our value of k, which we can then plug into our model. So u is equal to 22 plus 88e to this natural log 63 over 88 divided by 6 times t. They want us to know when, which is telling us we're solving for time, will the temperature be 50 degrees Celsius. So they're telling us what the value of u is. They want us to find the value of t. Start by subtracting 22 from both sides. 28 equals 88. E to this natural log, I'm just going to put that up there, times t. Divide both sides by 88. 28 over 88, I think we'll simplify that. 7 over 22. And now we'll take the natural log of both sides. I think I'm running out of space. Let me see if oh, nope, I don't have a blank slide. So I'm gonna have to erase some of this stuff so that I can get back to where we were. Or so I have more space anyway. So we've got the natural log, natural log of 7 over 22 equals just k times t. This natural log of e to the kt, that's going to cancel out from the inverse property. Our k was the natural log of 63 over 88 divided by 6 times t. And we can solve for t by dividing by this fraction. Now, dividing by a fraction is the same as multiplying by the reciprocal. So we can multiply by 6 over the natural log of 63 over 88 on both sides. When you multiply this out, go ahead and take a second, press pause if you need to. We should get t is equal to 20.559 minutes. Sorry for running out of room. Hopefully you guys can use your margins of your notes, or if you're writing on notebook paper, you should be okay. And our last application is going to be a logistic growth model. A logistic growth model is different from exponential growth and decay in that logistic growth is actually limited. The growth of the population is limited. Now, I love the discussion of limiting factors and what will limit the growth of a population. But since we're not face-to-face, I'll just give you guys some examples. Resources. If a population is running out of food, then it can't grow. Competition. If there are multiple populations fighting for the same resources. Space is an example of a resource. What else? Lots of different things can limit the growth of a population. The logistic growth model, P of t equals c over 1 plus a e to the negative bt. A, b, and c are just real numbers. T is time. Now, of these variables a, b, and c, c is very meaningful. C is the limiting size of the population. If we think about a new restaurant that opens up, there are laws that limit how many people can be in a room and still have it be safe for fire hazards. If everybody keeps coming in, eventually it's going to limit out to that carrying capacity. And they're going to have to wait for people to leave before more people can come in. But if it's a new restaurant and it's really awesome, there's always going to be that constant value, that limiting value of patrons there. So that's what our numerator represents. For a logistic growth model applications, like we see here, you're always going to be given the function. You're never going to have to model it like we have in all of our previous problems. It'll just be here for you, and then you'll start answering questions based on that function. So if the populations of cats in my gnome garden grows according to the following logistic growth model, how many cats can my garden support? What that's asking is, what is the maximum number of cats that I'm going to have in this gnome garden at any given time? And that's your value of C. That's what C represents. It's your limiting factor or your carrying capacity. So there can only be 84 cats in my gnome garden at any time. There's just not enough resources for any more than that. What's the initial population of cats? Well, this isn't set up just like our other models for exponential growth and decay, so we're not looking at just that lead coefficient like we were then. We actually have to solve for our initial population. But if we're referring to the initial population, what is the value of t? Well, initially t is 0. So we plug in t equals 0. And negative 0.07 times 0 is still 0, so I just substituted that in. Now I can simplify. Again, the more mental math that you can do, the less you rely on plugging all these complex expressions into your calculator, the more likely you are to get the right answer. So we have a numerator of 84. This is 1 plus 11 e to the 0. What is e to the 0 power? Well, anything raised to the power of 0 is 1, so this is 1 plus 11, or 84 over 12, which is 7. There were initially 7 cats in my gnome garden. How many cats are present in 5 weeks? So now we're plugging in t equals 5. Negative 0.07 times 5, negative 0.35. Simplifying, again, a little bit as you can go. You're going to want to evaluate your denominator first and then take 84 and divide it by that. We get about 9.958, which we will round up to 10 cats. Now, again, the reasonableness of this answer is very easy to check. We know that you can only have a total of 84 cats. So if you ended up with a number that was so astronomically large, beyond 84, then you've made some type of a mistake in typing this into your calculator. So 10 cats after 5 weeks. With these applications of exponential and logarithmic functions, a lot of times the first thing you're going to have to do is find our k. That's your growth parameter, your growth factor. Unless it is very specifically stated that you're given, or stated that you're given the value of k, you're going to have to find k first. Remember, we set up 2 ordered pairs and plug them into our model, and then we can solve an equation to find k. Once we have the value of k, then we can solve whatever question it is they're asking us to find. We looked at Newton's law of cooling, so the rate at which an object is cooling based on how hot it was cooled to or heated to and the temperature of the environment. We looked at logistic growth models. That's a growth model in which the population is limited, the growth is limited. And then we also looked at, first thing we looked at were our financial models, our compound interest. Now, with these problems, the models will be provided for you. So I'll give you the compound interest formula. I'll give you the continuous compound interest formula, our exponential growth decay model, and Newton's law of cooling. Again, with the logistic, the function's going to be given anyway. You're not modeling them. But I will not give you what the variables represent or how to use them. So no, you don't have to memorize them, but it is still important that you know how to use them and then how to solve these problems. I encourage you guys to get a lot of practice with these types of problems. The more you practice, the easier they become. And if you only do a couple problems, then when you show up to the problem or on the exam, you're more likely to just throw in 2 for a problem that says, oh, the number of posts doubles, instead of actually solving for K. Thank you guys very much. You guys have done a great job this semester. This wraps up college algebra, and this will get you ready for pre-calc, which you'll be taking next semester, where you'll kick off going over all of these concepts all over again. So hopefully you guys took really great notes, and thanks a lot for joining me this semester in college algebra. Have a great semester. Thanks.